So, as many people know, nuclear power is one of the world's most efficient and clean sources of low carbon electricity. However, we can't just produce energy out of nowhere, so the backbone of this introduction comes from a particular isotope of uranium, that being uranium 235. This element's unique properties make it an essential resource for sustaining the increasing global energy demand. Over the last century, uranium has become one of the world's most critical actin-side metals. Uranium is a naturally occurring element that has traces almost everywhere in Earth's crust, with an average concentration of 2 parts per million. For comparison, that is more than elements such as gold, silver, or mercury. Once the uranium deposits are identified, the extraction process is not much different than other materials. There are two traditional viable mining methods: open pit and underground mining. When ore bodies are close to the surface, they are best accessed by open pit extraction, which involves the removal of all the overburden and waste rock to reach the target uranium. The second method, underground mining, is utilized for deeper ore bodies. This involves the construction of shafts and tunnels, resulting in much less waste rock. These two mining techniques ensure that uranium can be accessed from shallow and deep deposits. A third non-traditional method can be used for the ore bodies contained within aquifers. This is known as situ leach mining. It involves dissolving uranium and pumping it out. However, this method can only be done where the aquifer is confined vertically and the potable water supplies are not threatened. When done correctly, this mining method does have the least amount of environmental impact, so it does provide an effective alternative to traditional mining. However, before the uranium can be used in fuel rods, it has to be enriched. The nuclear fuel used in a reactor needs to have a higher concentration of the U-235 isotope than what naturally occurs in ore bodies. Because when the uranium is mined, it consists of about 99.3% uranium-238 and 0.7% uranium-235. And in order for the uranium to be usable in most reactors, it needs to be enriched from its natural concentration of 0.7% to 3 to 5%. And then some specialized reactors need as much as 7 to 20%. And in order to get the desired ratio of different uranium isotopes, a process known as gas centrifuge is utilized. To simplify it incredibly, the uranium is converted into its chemical form, hexafluoride, also known as UF6, and this exists as a gas at a viable operating temperature. The gas is placed in a cylinder and rotated at a high speed, and then the centrifugal force creates the heavier molecules like the U-238 to move to the outside, while lighter molecules such as the 235 collect closer to the center. Then the gas closest to the center is withdrawn and fed into another chamber, and the process is repeated until the desired concentration is acquired. Once enrichment is complete, the uranium is processed into small pellets and then stacked into metal tubes known as fuel rods. In order to form a fuel assembly, a little over 200 of these rods are bundled together. Typically, a reactor core is made up of a few hundred assemblies, depending on the target power level. Once inside the reactor, the nuclear rods are submerged in about 6 meters of water. The water acts as both a coolant and controller of the fission process. It's important to slow down the neutrons produced in order to sustain the chain reaction over time. For additional oversight, control rods are then inserted into the reactor core, which can either increase the reaction rate or reduce it depending on what's needed. Fission creates a substantial amount of energy, which then turns the water to steam, which spins the turbine to produce electricity. Together, these components allow reactors to convert nuclear fission into steady, reliable electrical power. Due to the nature of radioactive elements, such as uranium, they cannot be utilized for energy indefinitely. I'm not going to go into all the science behind it, but fuel rods tend to last somewhere between 3 to 7 years, depending on the reactor. Many reactors use a rotation system where about a third of the rods are replaced at a time to keep the average energy output relatively the same. But once fuel becomes too depleted for efficient power generation, it must be carefully managed to protect both people and the environment. The United States alone produces around 2,000 metric tons of spent fuel each year, and the depleted uranium is either stored as UF6 or converted back into its natural state, making it suitable for long-term storage and lowering its toxicity. Currently, the nation's depleted uranium and other associated radioactive byproducts are initially stored in steel-lined concrete pools surrounded by water, and then eventually it's removed from the pools and placed in dry storage casks that are made of protective shielding materials such as steel and concrete. For the immediate future, the spent fuel rods can be safely placed at the reactor sites themselves, but as of now, there's no permanent disposable solutions determined by the U.S. Department of Energy, at least for the U.S. Some other countries, such as France, do have set locations where they can put radioactive waste. But depending on the conditions, depleted uranium can be recycled to make new fuel and other byproducts. According to the U.S. Department of Energy, like 90% of the potential energy still remains in the fuel. So the depleted uranium can be used in mixed oxide fuel. So basically, it's just mixing that with plutonium and it creates another type of energy source that can be used. And then due to its high density, even has various military applications. I'm sure a lot of you guys have heard, countries such as Russia use uranium depleted rounds to make like armor-piercing projectiles in the form of like solid slugs or penetrators. This is commonly used in the Gulf War and the Kosovo War, but it still has viability in modern warfare. So uranium does remain one of the most significant resources in the modern energy industry. Its ability to power reactors cleanly and efficiently highlights why we continue investing in its mining and enrichment. Advancements in recycling and mixed oxide fuels show that much of the uranium's potential still remains unused, and I believe that uranium will continue to be a key element as long as nuclear energy is utilized to make a clean electricity source. Thank you.